Okay, fantastic. So we understand and we appreciate where all of this comes from now. So this system here is not falling out of the heaven, but it's really just a very basic kind of derivatives, etc. that we're taking, setting stuff equal to 0, understanding why we can set it equal to 0 without having to force off the fact that we look at the second derivative being positive, like you would typically do sort of in when you solve for the roots of all quadratic equations. Okay, so this is essentially what we have. The finite element method does exactly the same thing. It just packages it slightly differently. So this integral approach that we've looked at, you understand now that we could fit functions this way, and you'll be now in a position to solve the homework example problems quite easily. Those first couple of problems that I've put up there. This is really just to make sure that we're comfortable with what's involved and see that we need to do lots of integrals. Okay, so that is one of the aspects. So this was essentially the system of equations that we had. Okay, so I'm writing it slightly differently here now. I'm just taking the negative that was negative x squared, negative x, and negative 1. If I pull it to the front here, I can pull them out. And then I can say, I could rewrite this derivative of e with respect to a, e with respect to b, e with respect to c. It's still the derivative of the same of this arrow squared. Yeah, that's essentially, of this residual squared, also the difference squared. That's really what this still means. But I'm just pulling out the negative 2's, yeah, and then I end up with something that's x squared, x, and 1, and I end up with the residual that's in here, because this is essentially residual squared, so that's 2 residual times the derivative of the inside stuff. That's really the way we've been taking the derivatives of this. This is the expression that we end up with. And so what the weighted residual method does is to say, wow, okay, if this is the case, okay, then I could maybe say, let's repackage this optimality criterion. This is what it's called. The fact that I'm setting the gradient equal to 0 is what's called the optimality criterion. Well, let's repackage it slightly differently. So the weighted residual method says, let's take this residual that we had, exactly the same residual as here. Okay, and we can see it's multiplied with the x squared, it's multiplied by x, and it's multiplied by 1. And this x squared, x, and 1 was essentially the shape and the form that we chose from G. Yeah, so G was a x squared plus bx plus c. Okay, let's bring in a new function that didn't exist before. We're going to call this function w. It's going to call our weighting function, and we're going to choose it the same form, exactly the same form as the g of x. The only difference is we're going to not call it the coefficients a, b, and c. We're going to call them new things now, and we call them here just d, e, and f. But the shape is exactly this. X squared corresponds to the shape of this g of x, which was also x squared. That was just ax squared here. This ex corresponds to the bx. The f is a constant and corresponds to the c, which is a constant in this g of x expression. This is important to understand. So I'm bringing in a new variable, a new function, a new field. It's called a weighting function. It's got exactly the same shape and the same form as what I have for g of x. And this, when I make this choice of exactly the same weighting function, I am now doing what's called the Bipnov-Galerkin finite element method. It's a hell of a fancy word for an extremely simple idea. Okay, so we're doing now Bipnov-Galerkin finite elements. Okay, this is what we're buying with this. But why would we want to do this? I mean, why would this even make sense? Well, the fact of the matter is, if I package it like this, okay, I bring in this new variable, and I just think of this as, so I'm going to repackage this. I'm going to think of this as the residual, which is just exactly what we had here, multiplied by dx squared plus ex plus f. 3 new variables. So now I've got something there's 6 things unknown, the a, b, and c, and the d, e, and f, okay? But if I do that, and when I want to try and understand what is the system that I need to try and solve, yeah, to get to this system that I want to try and solve, if I package it this way, I can now say, let's take the derivative of this new residual that we've created with respect to the variables only of d, e, and f, the variables associated with the weighting function. And if I do that, I recover exactly this expression here. Yeah, because we can just multiply by the minus 2 because it's all equal to 0. I then recover this system that I would like to solve to be satisfied, which is now a system where I need to solve for the a, b's, and c's. So this is what the weighted residual method is about. It's solving an error squared, yeah, but it's packaging it in a fancy way, in a different way. But this is important to understand this link, that when you solve for this, when we write the residual multiplied by some weighting function, and we take the derivatives with respect to the variables of the weighting function and set it equal to 0, we end up with a system of equations, yeah, that we essentially want to solve to set equal to 0. This is essentially, this is this system just packaged sort of still in the sort of integral form. Okay, and this then ends up with a system of equations that we want to try and solve. This is important to understand. Okay, and the nice thing is what we see here is when we solve the system, in the end, this packaged system, it's just a 3x3 system that we solve, similar to this 3x3 system that you got here for when we solve the discrete approach. Remember, this was also a 3x3 system and a 3x1. What you get here is a 3x3 and a 3x1 system. I forgot to make this point in the previous video, make this point hard. But this system, the same size as nice 3x3 systems, we can now solve them beautifully, and everything is hunky-dory. But the weighted residual method is really just doing this integral approach that we've done sort of brute force, yeah? And just say, let's just package this optimality criterion condition, this condition, in a different way by bringing in a weighting function. And if I take the derivatives of the weighting function, I recover the system of equations I need to solve to get my A, B's, and C's. And this is weighted residual method, and that's also one of the methods that's covered in the prescribed textbook. It's briefly covered, but this is the alternative to all these other approaches that are there, because there's also some energy approaches, some variational approaches. And what I like about this approach is we know exactly what we are doing. We have now, once we've solved this system, even whether we solve it now in this weighted residual approach, with this weighted residual approach version, or whether we solve it with just the sort of sum of the differences squared and taking derivatives in that space, we have solved sort of for the solution of this approximation that best describes the thing that we want to try and describe. And this is going to be our vehicle to drive forward. This weighted residual method is our vehicle to drive the finite element method forward. Okay, so hopefully this is something that you can go back to, and this idea of a weighting function is the central idea around which the finite element method is built.